back to the beginning. Last week I did a presentation, and I stressed this. It was about antennas, the concepts of how antennas work, what we look for in an antenna, its characteristics, how we might choose one, and all that kind of thing. And I used a modelling program to demonstrate those characteristics of an antenna. And I won't go back over it completely, but some points that I want to re-emphasise tonight. We need to, things that we might consider about an antenna, apart from the electrical, radio characteristics. There's a list of characteristics that we might think about. Physical characteristics, the size, the weight, mechanical complexity, wind loading that they apply to any support structure, the height of the antenna, suitability to harsh climatic conditions, multi-band capability where it might be required, and as hams we often would like that if it's possible. Ease of assembly and disassembly, especially for portable antennas, and always cost.
And another one you might want to add to that. Recently, unfortunately, we've got a brand new brood of magpies sitting on my tree.
Well,
Flora and Flora.
Yeah. Network 2. Do I allow this? Do I want to, Nick?
Yeah, it's okay.
Because it won't progress any further. So there are a few things. Okay. So how do I go on to the next slide? There you go. From the electrical point of view, or RF point of view, the things we might consider about an antenna would be its efficiency. And by efficiency we mean how well does it radiate, how much of the transmitter's power is actually radiated as electromagnetic waves rather than lost in heat, in losses and things like that. The radiation pattern is important. Where does it spray the signal? Does it send the signal in the direction or directions that we want? And that direction might actually be all around the horizon, an omnidirectional antenna. That's still a radiation pattern that we might desire. Polarization, vertical or horizontal, not just because the polarization of the receiving and transmitting antenna might need to match. It doesn't always need to match. Like for ionospheric paths, it doesn't matter. But to take advantage of certain propagation types on the very low bands for ground wave communication, we need vertical polarization. Horizontal doesn't work very well. Actually, it works very poorly. And feed point impedance, because we need to somehow match that antenna to our transmission line. Alright, so I'm not going to go through all these things. That was last week's talk. And that was by way of preparation for tonight's presentation, which is to look at these characteristics as they apply to an antenna that took my fancy, and I thought, this looks strange, I wonder if it would actually work. So the first step was to model it, to see whether the software said, yeah, it's got half a chance of working, and it said, yes, it should be fine, and then go and build it, which I did, tested it, and I've got it here tonight, or its bits here tonight, which could be assembled, and I'll take you through that. So I'll be showing the modelling part of it, and the thought process that led to the construction of the antenna. So I'm concentrating on an antenna mainly for portable use on 40 metres. One of my favourite HF bands because, well, it's an interesting band, right? And a lot of people use 40 metres, particularly this time of the sunspot cycle. It's still got some life in it, but it's a great band for, for working around Australia, the near Pacific, and also the world. Okay, 40 metres, we're talking wire antennas. So it'll be a wire antenna, and any way you cut it, it's going to be, it's going to be a tangle of wire. Excuse me. Half-wave dipole will be about 20 metres end to end. Quarter-wave vertical will be 10 and a bit metres high. and then you'll need ground radials and stuff like that. Okay, so it's not a compact antenna. Could we make it more compact? Well, my interest was piqued when, just over a period of time, I became aware, looking around on the internet, of various antennas where people have used some interesting schemes for reducing the size of the ground radial system. So just to show you, here's an installation. How come we're not seeing that? How come I'm seeing it on the computer, but you're not seeing it on the screen there?
Shrink down.
What happens if I get rid of that?
Well, that's better.
Okay. So there's a vertical antenna, possibly quarter wave vertical, I'm not sure. But you can see it's got a ground radial system installed on the surface of the ground, and there would be, I don't know how many there are, but a substantial number of radials. Could well be the 120 radials surrounding the antenna, and ideally they're half a wavelength long, so that could be for 20 metres, so it'd be twice that size if it's for 40 metres. It's a lot of wire on the ground, and you're going to get tangled. No way would you install this for a portable operation, It'd take you the entire weekend just unravelling wire, and then you've got to pack it all up again. And you probably wouldn't install it at home either these days on small suburban blocks. So, it's not practical, but that's what we're looking at as our...
Can you want to be on a hill, not in a valley?
Yeah. So as our fundamental antenna, that's what we would be looking at for a ground-mounted HF vertical antenna. Okay, so not practical. The vertical part is not a major problem. Like 10 metres high, pole 10 metres high. We could do something. I've got a squid pole that was 10 metres high until the end bit broke off. So you could do that, but the radial system is just not practical. So could we reduce the physical size, or are there other schemes we can employ? This is a picture of an old picture of a very low band antenna, and what you don't see probably is the vertical bit down the middle, which is a wire. Looks right down the middle there, which will be a shortened vertical antenna, but it doesn't use a ground radial system. It uses this, it's called a counterpoise. It's a system of wires insulated and suspended above ground. And there's a similar one up the top which forms a capacitance hat. The effect, and the antenna is connected to the top, middle of the top one, and the bottom one acts as an artificial earth. Effectively, it's got a lot of capacitance to earth. It's like having a connection to earth, but instead of having a physical electrical connection to the ground, there's a large capacitance due to the counterpoise. Okay, so
Chas, what's the Y-shaped structure then?
Just a holder? Just a holder.
well, that just to stop the thing, the top bit from flapping sideways. It's only on one side, but that's enough to do that. Or actually, it might be. That's too close to the tower, isn't it? Could be. Anyway, whatever. That's the concept. I don't want to dwell on this because we're never going to build anything like this. If Ken was here, he would wax lyrical about counterpoises, and it's a legitimate way of doing things. On 40 metres, it would not be anywhere near as onerous as this. Who knows? This would be very low band stuff from the early days of radio. Okay. Could we shrink it some more? we could build a quarter wave ground plane. Let me just go up a little, which I did some time ago. No, it's not that one. My eyeballs don't work that well. That's a squid pole.
Before you broke it, huh?
Oh, bungee cord.
Yeah. Let's magnify it up. And you can see the ground radials. They're suspended about 1.2 metres above ground using, maybe you can just see it over here. They're just garden stakes, 1.2 metre ground, earth stakes, insulator at the end. Now these radials should be, if it was a true quarter wave ground plane with quarter wave radials, they'd be about 10.5 metres long. I was experimenting with shortened radials here, and I won't go into the operation of that, but they're only half the length. And there's a compensation scheme going on here, so I won't worry about it. But originally, I didn't take any photos, but originally I had it set up with 10 plus metre long radials, so 4 radials elevated above ground. Worked fine. But again, how practical is that? Could you set this up in a portable capacity where there's people who are going to walk into the wires? You can't see them very well. Sure enough, someone's going to walk into them, get tangled up. I do myself, and I know that they're there. All right. I have another picture of it. Same thing. Anyway. So elevated ground radials, there's been some work done, experimental work done, that shows that elevated ground radials, only a few radials elevated above the ground, can be as efficient as a reasonably extensive radial system of wires laid on or just buried below, slightly below the surface of the ground. So it has its merits, especially if you want to take a portable. All right, so with that in mind, let's proceed. Still not ideal. Okay. And looking around on the web, I kept coming across photos of antennas that people have constructed using various schemes for making the radials or radial system smaller and smaller by coiling a single radial. So here's one example. It's a vertical antenna, there's a base loading coil there, so let's not worry about that. That is one single earth radial wound spirally around and supported on PVC conduit. I thought, that's interesting, but it can't really work. There's been nothing new invented there's nothing in the last 100 years that hasn't been known about antennas, so what's going on here? And they always claimed that they could make fantastic contacts with it and all the rest of it. I thought, well, yeah, interesting. So park that idea. Someone else took it even further. And this is for 20 metres, is coiled one radial. He's made that out of adhesive-backed copper tape on a bit of Lexan, I think it is. So it's just a spiral terminating nothing, so his earth connection is in the middle there. And here's a picture of it. Yeah. Okay, so you can see he's got a connection to the centre there. That's his earth. And the other bit is the vertical bit of wire there. And he claims it works. So again, I'm a bit sceptical about it all. But I thought, well, let's try something like this. So I said about designing an antenna. Well, first of all, I said about modelling an arrangement similar to this, and to see, does at least the modelling software tell me something about whether it's going to work or not. So off we go. I started with a model of a 40-metre ground plane. So here it is, modelled on Managel, which is Minineck 2 based program. So 4 radials and just about 10.5 metres long each, you can see that there. So 4 of those. And a vertical radiator, also about 10.5 metres long. It says 10.3 there, that's because there's also just so I can put my feed point here, there's a 200 mil or 100 mil long bit of wire in there. That red dot is the feed point where there's a mythical signal source applied. The program allows you to do that, and so think of it as the SO239 where the rig is connected, okay, or a rig connected right at that point. Okay, so I've constructed that model. And it's a classic quarter wave ground plane. Could be for any band. These dimensions are for 40 metres. You will do the same thing for 2 metres. Look around, you'll probably see VHF ground planes that look just like this. Okay, so here it is. Let's calculate it. Why didn't it say 40 metres? 7.15. Here we go. Now, I'll put it 1 metre above ground. Let's hit it. There you go. So it tells me 37 ohms peak point impedance. Ground plane should be about 36 ohms, something like that.
Yeah, half 74.
It's very close to resonance, only 2 ohms of reactance. That's pretty good. Let's look at its radiation pattern. Does it fling the RF around the way we expect a ground plane to do? Now, this is looking down, bird's eye view, the antenna is, and we're looking down on the antenna there, and we're seeing the field radiation around the horizon, if you like. So if you were at a long distance from this antenna, flying around with a helicopter, measuring the signal strength at a constant distance, and you call that 0 dB, you can plot it and you can see it's a perfect circular radiation pattern, which is characteristic of a ground plane antenna. The plot on the right hand side is, imagine you're on the ground looking through it, and you just took a slice through this and you look at it and we see this. So this is really kind of like donut shape, but we've taken a cross section through it. So again, classic ground plane radiation pattern. It's spraying the signal out around the horizon, not much going straight up, in fact nothing going straight up, but there is some high angle radiation there, a long way down. our grid references are in decibels, so minus 10 would be 1/10 of the power. So at this angle here, what's the angle? 70 degrees. We're down 10.3 dB, so only 1/10 of the signal is going, 1/10 of the power is going up at high angles at 80 degrees. Most of it's going out at 15, 20 degrees, something like that, which is what you probably want for a DX antenna, get that angle of radiation as low as possible. For more general, more local contacts in the 100 to 500 kilometre range, perhaps not so good, but at least we see that this antenna is behaving the way we expect a ground plane to behave, and it serves as our point of reference. So if you wanted to visualise a three-dimensional radiation pattern, that's what it looks like. Okay? So there's our basis. So let's have a look. If we fiddle around with this antenna a little bit, whilst I'm here, I might as well discuss this part because it is important. The blue and red lines show the current distribution on the antenna. Now, current is really important. It's an RF current. We're shaking around the electrons at the operating frequency. It's not sort of flowing like DC. We're making those electrons jiggle around. You can see, you can think of these lines, the current distribution graph, as a graph showing that maximum current occurs at the feed point, right at the base. The distance away from the radiating element is a measure of the current, and you can see it tapers away to nothing at the top, which is what you'd expect because you can't make current flow into nothing. You could, if you've got a big enough arc, I suppose.
Splice line.
Yeah. Oops. Let's turn the antenna back up again. Another point to look at is the blue bit. Red is shows the vertical current, so that's responsible for the vertical radiation pattern of the antenna. Blue shows the current distribution in the radials, and they're horizontal wires, so that would give rise to horizontal radiation, and up close to the radials you would actually detect a horizontal electric field. But an interesting thing, if you look at the diagonally, whatever, opposite radials, you see the current in this radial here, it shows the blue line under the wire, and on this one, it's above the wire. Now that's the polarity of the current. What it's telling us is that the current is equal and in opposite directions in the two radials. Same with the other pair of radials, equal and opposite. So at any far enough distance from this antenna, the net contribution to the radiation is zero. It cancels out. Up close you could measure the electric and magnetic fields of those radials. But at a distance, they add up to zero because the currents are in opposite directions and therefore radiating opposite polarity. Polarity is probably not the right word, but opposite phase. So diametrically opposite ones always cancel. Hence, this antenna, let's go to the far field plot so I can actually separate the vertical. That's the total radiation pattern, but if I look at the vertical and horizontal, you'll see there is no blue in the radiation pattern at all. And maybe just the tiniest bit, very, very close to the antenna, so over 50-something dB down. Okay, so that's all there is for the horizontal. So 100,000 of the power. All right. So what would happen because we're trying to arrive at a simple antenna. What would happen if I eliminated two of the radials? Wire number 4. Can I delete it from this? No. So that's wire 4, this is what, wire 3. Okay, so let's get rid of wires 3 and 4. Okay, so now I've only got 2 radials. What do you think's going to happen? How would the radiation pattern change? Slight change in feed point impedance. So we haven't got perfect calculation of the cancellation of the horizontal pattern anymore, but when we look at the 3D far field plot, pretty much the same as it was. Okay. What happens if I get rid of one more?
You right click and delete on that, I think.
No, I don't think it's got a delete function. So wire number 1. Okay, let's get rid of wire number 2 actually. Alright, so I've only got the vertical and 1 wire now. What do you think's going to happen?
Impedance changes.
Quite a lot actually. Because now we haven't got cancellation of the horizontal radiation of the of that remaining radial. Still a long way down at that angle, but when we look at it, it's sort of distorted the pattern a little bit. But still, essentially, not very different from what we have as a perfect ground plane. You see that this distortion, instead of being directly up the null, it's not a deep null anymore. Still a long way down, 13 dB or so. And there's a little bit of horizontal radiation there. Mind you, that's at a very low angle. If at, 21 degrees? If we look at about 45 degrees, you see there's a lot more of that radiation. And that's what we expect when we look at the 3D far field. You know, let's make it a bit bigger. Okay, so you can see it's spraying some at higher angles there. But essentially it's still a ground plane.
Show the blue horizontal field.
I'm not sure whether it actually does. Yes, it does.
Right hand side, just choose horizontal line.
There's your horizontal
Yeah.
pattern. There's your vertical under pattern. And of course, the total is a combination of the two. Alright, so anyway, it looks like even with one radial, looks like it's got half a chance of working. Okay. And what about if we coil up the radials? wire number 8. Number 8 is not vanishing. Okay, so I've got a ground plane. I'll make this vertical bit 10.4 metres long. So we've still got a ground plane. Now, I did that. Bear with me. I'm trying to change things on the fly here. What wire is this? Number 7. Okay. So I'll change it. What I did was I changed its length, and when you change the length from that particular function, it actually makes it longer at the top and longer at the bottom. I just want to make it longer at the top. So I'll change it here. Z2 is the height, so let's make it 10.4. So that's better. All right. Now, looking at that radial, remember I had that one radial out in a straight line. What I've done here is coiled it around. So from the base I've taken it out a certain distance, about 1.6 metres roughly. And I've gone around in a square and it finishes here. And you can see that there's a gap there. Alright, goes nowhere. So it's just been spiraled, it's just been coiled around. Right. Let's try it. 36 bit ohms. It's interesting, isn't it? Very reactive, it's capacitive actually. So the far field plot.
It's going to work.
Seen this before? Quarter wave ground plane with 4 quarter wave radials. Looks the same. How about that? I've got a metre above ground. If we look at the, I'll come back and remodel it in a minute. Current distribution. Let's just wind the currents back a little. Again, we see the red currents there on the vertical radiator, and the current on the horizontal. This is a bit hard to visualise, maybe. With a single wire, and we got the vertical radiator there. The current distribution was maximum at the base, tapering off to 0 at the end. Now, when you take that and bend it around into like a square shape like that, so does the current distribution go around. The interesting thing is that you can see the way, for the dimensions that I've chosen, if you look at the opposite sides of the square, you'll see that on this side here, the current is, say, in the positive direction. On this side here, it's in the negative direction. This side, on this wire here, the current is positive, on this side it's negative. End result is that you get substantial cancellation of the radiation field from that radial. You can see, looking just at the horizontal radiation pattern, you can see that it's more than 40 dB down on the vertical. The vertical pattern is our reference, 0 dB. Our horizontal is over 40 dB down, probably about 43 dB. What does that mean? Well, every 10 dB is a tenfold reduction, minus 4 in the negative direction. So 40 dB